So I did so I did so BA3 and
All right. Good morning, guys. So yesterday, yesterday you guys should have watched the video on writing formulas and names for ionic compounds. Okay, so that's what the warm-up is, just reviewing the stuff in the video yesterday. Today we were just like adding a little bit to it, and then it's mostly a work period just to make sure you've mastered this. Your digital learning for tomorrow will be a quiz on this, so an online quiz. Try to, obviously I'm aware I'm like assigning quizzes online at home. I'm obviously aware that you have different resources than if you were taking a quiz in class. One thing that I noticed when I was looking at some, like the old quiz like last night that I was grading, it's very obvious when you just copy and pasted from the internet, just saying. So, give it a go. I give you 2 chances. Give it a go on your own, just trying to use the stuff from class. If you feel like you need an extra chance, let's say you like struggled with it first, got some wrong, did it the second try, then for some reason, hours later, it clicks. Like I can reset submissions for you. The goal is for you to learn that material. Does that make sense? I know that with an honors group, we tend to be very fixated on grades, but in this environment where you're doing half of your digital work and then half of it is here, like I just need to make sure you know it. So the quizzes are really there to just like assess your knowledge and see how we can get better, okay? And if that is you, let's say you didn't do well on that quiz and you need it to be reset, that's why I put in the grade book last night, make sure you just go and reset, like ask me, I'll give you another try and just give it a genuine like attempt. Does that make sense? Are we together on that? I get it? Okay. All right, so when we are writing, when we write these formulas and formulas and names for these compounds, the ones we've done so far are ionic compounds, which means what 2 types of elements are forming an ionic compound? Metal and non-metal, okay? And which type of those elements, so either metal or non-metal, tends to always be the cation? The metal, good, yeah. So the first one is always going to be the cation. You're right. The first one's always the cation, which is always going to be the metal. The anion will always be second in the formula remain, and that generally is the non-metal. Now today we're going to talk about when it's not a metal or non-metal, it's something called a polyatomic ion. So that's like the addition, the extra piece we're incorporating today. When we're writing names, you have to be aware, let's just kind of go out of order. Let's do this one first, okay, the very bottom one. That's the CAF2 is what we're going to go over first, and I'll come back to the top. All you have to do is just say the name as it is for that first one, that metal. So in this case, I just say calcium. All right, so we're going to say calcium. And then the only thing you're doing for that anion is you're adding an IDE at the end. So this is calcium fluoride. That's how we change this for an ionic bond. If we go in reverse order, so if we see AgBr, if you notice that the element is in the transitional metals, you need to go and check that transitional metal to see if it has more than one charge. So you take a look at your periodic table, this green one. We're looking at these transitional metals because silver is a transitional metal. Does it have more than one charge in that box? No. So I don't have to make note of it if there is not one. So this one is just going to be silver. And then what am I going to change this word to? Bromide. Good. All right. Then the first example is kind of the hardest one in this group because we need copper is a transitional metal, so we need to look at the periodic table, see which ones it could be. Copper can either be you see, look on copper, it's number 29. Do you see how that box is divided and it has two different ones? So copper can either be a 2+ or a 1+. If you have subscripts like we do here, we can do what we call a reverse crisscross to get that charge. So that means I can like bring this 3 up here for the phosphorus, and if there is not a subscript here, then that means it was a 1, right? So this is going to be copper 1 phosphide. If you don't have subscripts for that, so like the example, one of them we went over yesterday is like CuO. There are no subscripts, and again, copper, we just looked at it, could be a 2+ or a 1+. With there being no subscripts, you need to use the anion to balance this out then, because the overall goal is for it to equal to 0. So what is oxygen's charge there? 2-. Do you see that it's a 2-? And that means for this to balance out, copper has to be a 2+. So this one, even though it looks like it would be a 1+, is actually a 2+ here. And so I use my Roman numerals to write that, to display that to the reader.
Hey, you're just dropping off.
Oh, yay, yeah. Like a lot of things.
It doesn't matter. This is like my gun.
Right here?
This corner. I did all that, that's for me. Oh, well, thank you so much. I didn't know. That's it.
Got it. Thank you. Sure. All right. Have a good day. All right. So then we have the ionic formulas here. So this is where we're doing the opposite of what we just did. So we have sodium oxide, okay? And did anybody watch the video yesterday and see what was our shortcut for this? I called it a something method. A crisscross method is how we can write these formulas, and it's our shortcut. Again, ideally we need to balance out our charges here. So it means I'm going to look up each of their charges on that periodic table. Sodium has a what charge? +1. Oxygen is a 2-. So I crisscross my charges here, which means I just pull these numbers down as subscripts. You don't have to write it if it is a 1, and we don't write the charge itself. We don't write the plus or minus, so it ends up being Na2O. For calcium sulfide, calcium, what charge does calcium have? Does a 2+ charge? What about sulfur? 2-. So remember, the overall goal is to balance this out and the compound needs to be equal to 0. Do I need to crisscross my charges so that it will be equal to 0? No, it cancels out, and so you end up with CAS. We have barium phosphide here. Barium is a what charge? 2+. Phosphide, 3-. I crisscross charges, and I end up with Ba3P2. The things that you need to make sure you are aware of, these subscripts need to be smaller and at the bottom of the number. You cannot write them at the same size. Granted, on your quiz that you're supposed to take tomorrow, you don't really have the ability to do that via Canvas, so it will just be a regular size number. Make sure you're only capitalizing the letters that need to be capitalized. Like use the periodic table. You're given it every single time. Don't guess what sodium's symbol was, because most of you will guess that it's S, and it is in fact not S, it's Na. Okay, so we always want to make sure we capitalize that first letter lowercase is the second one if it has it. And yeah, like just make sure you follow those rules when you're writing formulas. Stella, do you have a?
Yeah. On the first like C or calcium fluoride two, why is there not like Roman numerals?
You only have to do the Roman numerals if it is a transitional metal and if that transitional metal has more than one charge. So you only have to do it for the ones that look like titanium, chromium, cobalt. Do you see how like in that first row here, the box is split with more than one?
Okay.
So what we are adding on to this today is going to be using these polyatomic ions into these formulas. So look at your green periodic table. You see that there's a table at the top. It is listed table of polyatomic ions. These are not all the polyatomic ions, but what they are is like a molecule in itself. So it's this group of atoms all bonded together, and the entire structure has a charge. So these can form ionic bonds just like our metals and nonmetals can. So we have to learn how to formulate and name those as well. So in order to do this, it's just on the back of the notes from yesterday. I have extra copies if you don't have them, so I'll walk around right now and print them or hand them out to you if you need it. It's on the back. So this is yesterday. The back was it. So I have plenty of copies if you need it. You let me know if I'm Oh yeah, I do. Okay. You have it, yeah.
Yeah, like where you're like, I remember that. I was in quarantine, remember? I'm really off. Since we get in like online, I haven't been like taking pictures. No, taking us like down in pictures and you're like, sorry, I said it's wrong. Like if they ask for it. Sometimes you can just like open it and you see like
It is like
yeah, exactly. Or I sent it to healthcare and then their screen was part of the worksheet. So I sent all three pages like overlapping like this. So like you would look like they're just
honestly, that's what like I'll be like, oh, hard work, I'll be able to do it all, and you don't even check it. And this other people would be like a super simple worksheet where they'll check every single letter. Like, if you even have a letter wrong, they'll take a point off. What? Oh, I was saying some of the stuff. I was like, for Spanish stuff, like, they'll take points off if you even get like a letter wrong on it. Which I mean, kind of makes sense because it's Spanish.
That makes more sense.
Yeah.
But that's why I was like really confused. Alright, let me see.
Well, I want to off the letter. They might get this house like 7 people.
All right, so again, we're only going over the back. Okay, the back is where we're at right now. The front is what we did yesterday. So it's the same process. We're still naming and formulating for ionic bonds, but this is for ternary. The other ones yesterday were binary. So this means we just have polyatomic ions involved. And so if you read the top, I don't actually have a slideshow for you. We are just going to go through examples, kind of like just jump right in, figure this out. But you do need this periodic table so that you can look these up. So these ionic compounds are going to have polyatomic ions in the compound. We still use the crisscross method, so that's still the same. If there's more than one polyatomic ion in the formula, then we have to put that polyatomic ion in parentheses, and the subscript will go outside of those parentheses. So in order to kind of show you how this works, I generally like to show you where I can kind of draw what we're seeing here. So sodium, I'm going to use, all right, so sodium we're going to say is this guy, all right? So that's the sodium. What is sodium's charge? Sodium is a +1 atom, okay? Now it is forming an ionic bond with phosphate. Find phosphate on that, on your polyatomic ions list. So that means that you need, hold on. All right, we're gonna act like for some reason it doesn't want to. No, it's fine. I just changed the color. I don't know why. All right, so phosphate is what? What you have to say the entire formula. What is the entire formula of phosphate? PO43 minus. So what that means is this entire what phosphate looks like. Phosphate realistically is going to be a giant molecule. It looks like this. Okay, and the entire thing, this entire structure has a 3 minus charge. Okay, so that's what phosphate is. But we're not there yet, so I'm just going to put it in a circle so you know that it belongs together. All right, the whole goal is to balance out our charges, right? So right now, are my charges balanced out the way it's written? No. What do I need to do to make sure we have an overall charge of 0 on this bond? Add 2 more NAs. Good. Because I have a 3 minus charge, I only have a 1 plus. So I'm going to have to add 3 more NAs to this. So I didn't do that even. I'm really good at clicking stuff today. So if I add 3 more of these, obviously it would do it in a more reasonable way, but 3 more NAs. Now I have an overall charge of 0, right? Are you with me on that? Yes. So then I would need, what is your question?
I was just gonna ask how you just like add them. Like you just like create new.
I mean, no, that's not what's going to happen.
Oh.
That's a good question. So realistically, what's happening is I've got sodium metal, I have some phosphate, and I'm actually going to combine them in a lab. You know what I mean? Like I've got grams of each, which means if I have grams of these substances, then I have millions of atoms in there. So I have probably like millions of these molecules, millions of these. So they're just like floating around. This is just how they're going to form a bond in a solution or any kind of reaction. Does that make more sense? Mm-hmm. So, yes, yeah.
Okay, so you're doing grams of each one, and you're obviously not going to go over these molecules in there. So if they all match up and you get to the end and you have like only 2 NAs, what happens? Then you just go up on, and then you just have a further.
Yeah. Okay. No, that's exactly right. That's a really good question. So, probably when we get really close to Thanksgiving, we go over stoichiometry, and it's exactly what you're saying right now. So you're thinking, one, that's awesome that like you've already thought about that sort of thing. We call the one that gets used up first, we're going to call that a limiting reactant because it limits how much product we can form. And then the other one that's left over, you'll just have some excess of one of them, and that's called the excess reactant. That means in your like solution that forms, majority of it's probably going to be your product, depending on how much you use. But let's say you didn't want to even measure it. Let's say you just like dumped in a whole bunch of them. Like you might end up having a ton of excess reactant in that same. So it's, I can like keep going down a road, but is that like,
Yeah.
okay? I was like, the way we do that a lot of times is we like filter off the one that we don't want, things like that. Does that make sense?
Yeah.
Okay. But that's a really good question. So, um, all right, so we need to write a formula that represents what we see here, okay? So our formula, how many NAs do we have? 3, and we have only how many phosphates? 1. But it is important for you to make sure you write the entire thing. Just because, like PO4, that 4 is a part of phosphate. We can't just take it away because there's only one of them. So this is realistically what we're writing. We need to show that there are 3 sodiums and 1 phosphate. Our crisscross method here, we can do the same thing. So on this side of my screen, I'm just going to use this crisscross method just to kind of show you what we already did. We have 1 sodium, and then we have phosphate, and we looked up that it was PO4 3 minus. So we are going to crisscross our charges here to get our formula, just like we did before. And so we still get that same answer of Na3PO4. All right. And since we only have 1 phosphate, we don't have to use parentheses in this example. Some of you will want, I realize that some students just want like a general rule. Oh, that polyatomic ion, I want to put parentheses around it all the time. I'm not going to count off for it in this class, but know that it's not necessary unless you have more than one. So this is the answer to that first example. So if we go to our second example, right, the second one is magnesium phosphate. All right, so if I have magnesium phosphate, all right, let's just make magnesium purple in this example. What is magnesium's charge? It is a 2 plus, good. So I've got this magnesium atom here, and it is a 2 plus ion, all right? Phosphate, we just looked up. I guess we'll just be consistent and use flat. So phosphate, we just found, remember, is PO4 3 minus. Okay, so it still has that 3 minus charge. It's like an entire package deal. Now, my question is to you, is this balanced? Like, is it equaling 0? How would I get this equal to 0? How many magnesiums, like, what is my number that I need to get these charges to? Like, I can't get 2 to be equal to 3. So I'm going to need to go for that, like, least common denominator, which is 6. So how many magnesiums would I need then? I'm going to need 3 magnesiums, good. So this is not realistically how they form. I'm just drawing them on the screen, okay? So 3 magnesium, and then how many phosphates am I going to need? 2, good. So this is what it's going to look like here. Again, not realistically, but so we get a point. All right, so now I need to draw what I see. So again, with my formula, I always write my magnesiums first. So that is Mg. There are 3 of them there, so I always write that subscript. And then PO4, So here's the thing. I can't change that subscript of phosphorus, or phosphate, excuse me. So in order to show there are two of them there, why would just putting a 2 here be wrong? Because it looks like I have 42 of oxygens and just one phosphorus. So I need to be able to tell the reader that I have 2 phosphates. So I do that by putting this guy in parentheses. It says everything here. This is a group, and I have 2 of them. Does that make sense? But we still can do crisscross. So this is just like what we see here. I just like to give you a visual representation of what we're doing. But if we do that crisscross method that we were doing yesterday and this morning, magnesium has that 2 plus phosphate, PO4 3 minus. I'm going to crisscross my charges. Okay, that 3 gets brought down, 2 goes behind it, and so we just rewrite it like this guy here. Okay, again with the parentheses. The biggest thing that people mess up is they want to take that 4 off of that phosphate and just put the 2 there. But it's wrong because you can't change what phosphate is. Remember that these are actual like things that we're representing. Yes.
So the only difference between that and is it binary? Is that what the other one's called?
The other one is binary, yeah.
Is the only difference between those two just that you still do the cross thing? You just use the polyatomic thing.
Mm-hmm. Yep, that's exactly right. Yeah. So same exact thing. We just have polyatomic. Okay. All right. Your next example, I'm probably not going to draw this extensively. I just want you to try. I'm going to give you a 30-second head start on trying to write this formula. So we have calcium nitrate. So you start by writing, you don't need to draw this, by the way. So the whole drawing thing was just so you got a visual of what we were actually doing. I just want you to start with the crisscross method. Okay, so find their charges and write the formula. All right, so calcium, what kind of charge does calcium have? A 2 plus. Nitrate, what is its formula? So be really careful. I think nitrate and nitrite get easily confused because they're sitting side by side. Nitrate, the ATE actually has one more oxygen in it, so it is NO3 1 minus. But nitrite is NO2. All right, so we are going to crisscross our charges. Do not touch that 3. Okay, don't change it. But we are going to end up with just Ca. We don't have to write the 1. What am I going to put NO3 in? Parentheses. So NO3 like this. And then this 2 goes outside of the parentheses again to tell you you have 2 nitrates there. Okay. It's not on your paper, but I just want to point out ammonium gets used pretty often. Why is ammonium, it's at the bottom right corner of that table. How is that different from all the other ones in the table? It's positive, which means is it going to go in the back? No, because cations go first. So anytime you have ammonia, like ammonium fluoride, you're going to write as NH4, and then you have F there. I just want to make you aware that it's the same rules that apply. And the reason why is they're both 1 plus 1 minus charges. They cancel each other out. You can put this in parentheses if that makes you feel weird, but it's not necessary because there's only 1. Okay?
Yeah. When you write the name, you also write that name first.
Yes. Mm-hmm. Yeah. So you always write the cation first. Yes, that's correct. Okay. So do we have any questions on formula writing? All right. We go to naming. Same kind of thing we do like we did yesterday. If we have a monatomic ion, meaning the monatomic means it's just 1 atom. So it means it's from this side, okay, the monatomic anion. We add that IDE to it. But if you have a polyatomic ion, it doesn't matter where it is in the formula, you never change the name of that polyatomic. Okay, we're not adding an ending, we just say what it is. So these are almost easier because all you have to do, especially if it's an anion, is just say both names like right them together. So let's see, we have NaOH is our first example. So what do we know? That first element is obviously called sodium. So if you see a group of atoms like that together, O and H is a polyatomic ion. We look for OH and we find that it is hydroxide. We don't change the name. We just leave it as it is, and so this is sodium hydroxide. This is that this is those pellets we use in that penny lab. This is what sodium hydroxide formula is. All right, we have KNO2. Okay, so for this first one, it is potassium. And then we look up NO2 to see that it is nitrite. Good, yes. That one is nitrite with a I. Again, don't change that ending, just leave it as is. And then our last example, the reason I have this on there is for you to realize that the thing with the transition of metals still applies. So we have, all right, gold, well, I just gave it away. The whole point was for you to name it. So the first one is gold. But what's special about gold? There's more than one charge, so it can either be a 1+ or a 3+. Since there is like an extra subscript, we can do that reverse crisscross. So I know that gold was originally a 3+. Okay, so I put 3 in Roman numerals, and then I just say nitrate. Like that. Do we have any questions at all whatsoever? All right, so the rest of the day is for you to practice. Okay, it is just for you to master this skill before you take your quiz tomorrow. So that's all I got for you today.